Am I audible in the back? Perfect. Okay. Uh, so what did we do in the last class? We looked at the layout of the memory cell. Okay. Before that, hmm, butterfly curves. Okay. So we had a quick review of the stability and how a butterfly curve can represent stability of a memory cell. So what is the metric of stability if you use a butterfly curve? How do you find that? The largest square that you can fit into the smaller lobe of the butterfly curve gives you an estimate of the stability of the cell. Now you can use the side of the square or the diagonal of the square. Doesn't matter. It represents the same thing. Hmm? So whether you use the side of the square or the diagonal of the square, it doesn't matter. It means the same thing. What is important is that you're talking about the largest square. And now we understand why largest square comes. Because if you had a little more noise, you would have moved from one lobe of the butterfly curve to the other side. Are you able to see that? Okay. Then what did we do after that? We looked at the other cell topologies, the 80 cells. There was this 80 cell, which is one read, one write cell, and there was the other 80 cell, which was a two read write cell. Hmm? So, what are the advantages of a one read, one write 80 cell? Why is this not coming? What are the advantages of that uh, decoupled read and write ports in the one read, one write 80 cell? Stability. What do you mean by stability over here? So when we looked at the stability curve earlier, we saw that uh, because a Vx appears, the noise margin reduces. Hmm. Therefore, there are clear constraints on how much we can size pass gate and pull down. There was the cell ratio that we said there has to be some ratio. Pass gate has to be more resistive than the pull down. We saw some such stuff. And because of that, we may not really be able to extract the speed that we want to extract out of the memory cell. As soon as you put a separate port for the read operation, now read current and stability are no longer coupled. Are you able to see this? So since you are now, and stability is the functional figure of merit. We looked at the functional figures of merit, the writability, stability, they are both functional figures of merit. You really can't violate stability criteria. So if stability has to be ensured at whatever cost, then you rather put an extra port and improve the performance. Hmm. So first thing is it takes care of the stability of the cell. Second is that while it takes care of stability of the cell during the read cycle, in a write cycle, the same cells also operate as in the read port. So अगर आपका mux 1 से ज़्यादा है, there are more than 1 bit cells in every row. When you select the word line, what happens? All the bit cells are selected. Now you are writing into only a few of them. So the read operation is still happening. So it doesn't mean that 60 part of the cell is independent of any read stability constraints. The 60 part of the cell, you still have to design exactly the same way as earlier. Are you with me on this? But yes, the extra two T's that you put, which was only the read port, that you can size up and have a better read current. And we also looked at the new figure of merit that would come in this case, which was called as I partial on. When does this I partial on appear? When the other port is also selected. You're writing, suppose it is mux 4, and you're writing on the adjacent address, adjacent cell. So your particular cell through which you are reading would be in read mode on the 60 port side. So there will be a Vx that is generated. That Vx will turn on the read stack a little. So there is some more current that is going to flow than just the leakage current. If this current is very large, then add leakage to it, your reading operation may fail. Are you with me on this? I see a lot of blank faces. You did not make the notes last time? Then? So what we are talking about is this is my word line. This is my WBL. This is my WBLB. And I have another word line, which I now call as RWL, read word line. Hmm? How is it used? It goes to the gate of another stack. And this is read bit line. कुछ नहीं दिख रहा होगा आपको. So now let us say this particular, the 60 part, the right port. So you have, let us say you have implemented it in mux 4. So in every row, for every word or for every IO, there are 4 cells, of which one of them you are writing. But the word line of all of them is selected. So the remaining all 3 are in read mode. So let us say this is one of those read mode cells, because obviously you cannot write and read from the same location at the same time. So the adjacent cell was being written into, and you are in the read mode. So what happens? Let us say there was a 0 stored over here, and this cell enters into read mode. This word line goes high. This 0 rises up to Vx. As soon as this rises up to Vx, this RWL was already 1, but earlier this was 0. So there was some leakage current, I sub, that I was worried about. But now there is Vx over here. It is no longer I sub, it is now I partial on. And this current is far larger than I sub, because in the subthreshold region, the current increases exponentially with the VGS. So even if that Vx is small, this current is far more than the leakage current that you had earlier estimated. So this is a new figure of merit that we have. Is this clear now? Any further questions about this? Okay. Then what happens to the other 8T cell, where you have 2 read-write ports? See, this was one cell which had only 1 read and 1 write port. In the class itself, we spent a lot of time discussing this and the partial on. But in the lecture, we've also discussed in much more detail about the other 8T cell. So what happens there? What are the new figures of merit that we are talking about there? So first, as Shivani mentioned, there is a clear, Prachi mentioned, there is a clear thing that uh, there are two read-write ports. Both ports can be accessed in parallel, just like here. We access both the ports in parallel with different address locations. In the same way, the regular or two read-write 80 cell can also be accessed in the same way. So the cell current now becomes dependent on what is the immediate constraint that you put on the cell current? It has to be higher if we are both reading at the same time. So now, if you want the same cell current, then the sizing of your pull down has to be much larger. Because pass gate, you can still keep the same size, but pull down is sinking current from two pass gates now. If pull down is not large, what will happen? First, there will be a constraint on the current that will flow. Second, the Vx will rise for both the ports. Are you able to see this? See, हम pull down को बड़ा क्यों बनाते हैं? Why do we make the pull down large? To sink the current with a small VDS so that Vx remains small. Now you make it small, make the pull down small. What happens? Now it can obviously sink the same current as pass gate is sinking. Why not? It's much bigger. It is still bigger than the pass gate. But what will be required? A larger VDS because you are in the linear region. A larger VDS means larger Vx. So cell stability will go for a toss. Are you able to visualize this? So that cell has a slightly different structure than this cell. Instead of this set being there, there is another set of another pair of bit lines now, and another word line also. And the same thing can happen. Both the word lines can get selected simultaneously. Now, both will try to sink current from the same pull down, and it won't work. Are you able to see this? It won't work. So you do not want this Vx to be large. If this Vx is to be small, then this pull down over here has to be almost 2x the pull down of single port cell. Almost 2 times. And there is a very bigger, it's a much bigger or a different kind of challenge that happens during write. What is that? So now let us say one port is writing on cell A, other port is writing on cell B. Both the ports are in write mode. So what will happen? Because I'm writing on cell A from this port, cell B from the other port, the other pair of bit lines on this port will remain pre-charged. So what is happening? I'm trying to sync. Now let us, I hope there is no other colored pen also. Now let us say that I want to write a 0 here. And I want to write a 0 from this particular port. What will happen? The 0 will try to sync from the write driver down there. Okay? But the other port is in the read mode and its pre-charge is on. So it is continuously pouring in more current over here. You are discharging some current from this right driver, but the other pre-charge is pouring in current from there. So you're not really able to write a zero also. So when it comes to a pure dual port cell, which is two read-write cell, the complexity goes multifold. लगता है कि हाँ एक की जगह दो ही तो है, but now those two ports, if they can be accessed asynchronously, the challenge is far bigger. Yes, Madhav, you had a question. The pre-charge will be off, right? So is it that pre-charge is off for the bit lines on which you are writing? So, I mean, you'll not. So there are two methods. So we have not done the IO circuit set, but we will come to it. So I will anyway talk about it right now itself. There are two ways to handle pre-charge. One is all pre-charge off. कहने का मतलब word line has come, bit lines are discharging. Because bit lines are discharging, let me turn off all the pre-charge. That is one way. What is the challenge with that? The challenge with that is, let us say there is this mux 4 again. Okay? There is this bit line, bit line, bit line bar, bit line bar, bit line, bit line, bit line bar, bit line bar. Okay? Let us say there was a zero stored over here, and I wanted to read this particular cell. Is it visible? There was zero stored in cell, the second cell over here, and I wanted to read it. Now, let us say there was a zero stored here and a zero stored here also. Just some data, it is random data, any data can be stored. Now look at what is happening. I have turned off pre-charge of everything. So over here, there is one stored. So this particular bit line will remain stable. This particular bit line, because I am reading this will discharge. This particular bit line, one was stored, it wants to remain stable, but the adjacent bit line is discharging. Coupling between these two will result in this also discharging a little. What has happened? Earlier, when we were looking at the figures of merit, we said bitline leakage is the one that will kill the differential between bitline and bitline bar. What has happened now? The coupling capacitance of the adjacent bitline is now also starting to impact your performance. Is it acceptable? No. So what you do? You do not switch off pre-charge of every cell. You only do selective pre-charge off. See, whoever told you memory is a digital circuit made a fool out of you. Now do you realize choti capacitances? Digital circuit, do you even bother about such capacitances? Did you ever think about such capacitances when you were doing DVD? Nah. Okay, delay में कुछ impact आएगा. Over here, look at it. You can actually end up reading wrong. So you do not turn all the pre-charges off. Pre-charge of only the selected bit lines is turned off. What does that do? That means that when I'm writing into this particular cell, the pre-charge on the other side is on. And that is pouring more current into this internal node. I was trying to save that current, but there is now a short circuit path from one pre-charge to the other right driver. Are you able to see this? As a consequence, what happens? Writeability goes for a toss. That's the figure of merit for the to read write 80 cell. Are you with me on this? Any questions about this? So many of you will probably take up a project on 80 cells, 60 cells, and whatever. So it's important that you understand the figures of merit really, really well. Because if you don't, the project is going to cause a lot of trouble to you. See, uh, what I have started to do based on your feedback is that I'm touching upon previous lectures in much more detail at the start of today's lecture. But what I'm surprised about is many of you told me, sir, नहीं नहीं पहले आप क्लास लो उसके बाद हम आपका लेक्चर देखेंगे. But I can see many of you have not even watched the lecture even now. Forget about today's lecture, not watch the lecture that I have already completed. So it was never about me asking you to watch the lecture earlier. I can see those blank faces. Yeah, baby. मैं क्या बात कर रहा हूँ आपको अभी भी नहीं समझ में आ रहा मतलब you not watch the lecture. It's entirely up to you. Yes, Prachi.
One thing, if Vx degrades too much, writeability also degrades.
If Vx degrades too much, right? Yeah, because if I wanted to write a 0 here and all this charging up and everything is happening, then my writability is already gone for a toss. There are too many variables that come into picture. So when you know, we did everything in a particular manner. Everything was clean, absolutely clean. Okay, and then we still had a silicon failure. And when we analyzed the failure, you know what we saw? We saw that because the two ports are asynchronous, word line of port 1 got selected at this particular time. Word line of port 2 got selected at this particular time. So this precharge turned off here. This precharge turned off here. Okay. But before this precharge could turn off, yeah, kuch, you know, something like that happened. Now, since this precharge is off, it already started to discharge. And there was a duration when both precharges were off. And even though I had taken care of everything in the static manner, the relative spacing between my clock 1 and clock 2 led to extra discharge on the other port, and I ended up reading wrong. It's a complex failure mode. I do not want to enter into that mode just yet. What I want to tell you is, कि जो अभी मैं बता रहा हूँ, that is still just the tip of the iceberg. In reality, because these are two asynchronous ports, two clocks can come at any point of time. The clocks are not synchronized. Asynchronous ports mean they are synchronous ports, but the two clocks are not synchronized. They do not necessarily arrive at the same time. And that relative spacing between the two clocks leads to new failure modes. So when we will talk about test and testability for dual port SRAMs, we will not talk about it much, but whatever we talk about, this is an additional test mode that we have to introduce in the memory. So that at the time of testing itself, I can estimate if there is any sensitivity to such asynchronous clock arrivals. So dual port is far more complex. In terms of cell area, dual port cell area is almost double that of the single port cell area. It enables you to do much faster. And so, see, those of you who have done computer architecture, when multiple cores want to access one particular memory or one particular data, if you have two single port memories, then there has to be a memory controller that does coherence. That's a huge burden, overhead, not just in terms of hardware, but also in terms of cycles in which coherence checks are being done, or all those things. There are halt states that can appear in the processor. If you have a dual port memory, on the other hand, those halt states and those synchronizations are no longer required. So there is an advantage of using a dual port memory. but it is also far more complex to design. And therefore, inside a design parameters को ध्यान रखते हुए जब हम बनाते हैं, so what happens is that the dual port memory is slower than the single port memory. So you wanted to avoid stall states and have overall better throughput. Now, since your memory is slower, throughput anyway goes for a toss. So those of you who go into computer architecture kind of roles, uh, understanding these failure modes in this particular course can help you design better architectures which will work in a more robust manner later. So this course, the memories are 70% of any digital SOC's area. So this course is not just about how to design a memory. You may never design a memory in your life after this course. But even then, the knowledge that you gain over here will help you be a good architect. Are you able to see this? So please, those of you who complained that, sir, पहले lecture दे दो, हम बाद में देखेंगे, and still not watching the lectures, I'm kind of covering every slide in much detail based on your feedback. But I don't think the result is going to be different if you don't change. See, एक दिन पहले देखना है, एक दिन बाद देखना है. The result is going to be the same. देखना तो पड़ेगा. अगर आप देखने ही नहीं वाले हो तो कैसे चलेगा? उसमें डिसएडवांटेज क्या है जो अलग अलग टाइम पे आ रही है? Yeah, so again, it's a very involved thing. We had to spend months to arrive at, okay, this can happen. I will just give you a very, very quick overview over here. You may not understand it just yet. There are papers which we published, which you can read, or which are there already in the literature, which you can read. So what happens is, I want to read from this particular port. I turn its recharge off. I want to read from this port also. So this port starts to read earlier, and this precharge is off. Suppose there was a 1 stored here. This bit line was not supposed to discharge. But the adjacent cell, there was a 0 stored. So there is coupling that has come even before. See, वही जो मैंने precharge का बताया, selective precharge वाला. There's a coupling that has already come before your read operation started. You're starting from a lower BL than VDD because precharge was off and there is coupling that is coming. Can you control what was written on the other side? No. That is a random data. So it can come in whichever way. So now the thing is, how early should first precharge come? How late should the second precharge come? Which row is being selected? So many things. In fact, in dual port memories, pure dual port memories, you have one port on this side, one port on the other side. So this clock has to travel from here, this clock has to travel from here. So even if they arrive at the same time at the inputs, for this particular cell, this clock will arrive later than this clock. You cannot do anything about it. You have to design such that in all such circumstances, your system still has sufficient margins so that it doesn't fail. I do not want to overwhelm you. You're just entering into the waters of SRAM design. But I'm just still telling you that if you do not understand these very fundamental foundational lectures that we are in these few days, then all these important things that, see, in life, do you think you can make all the mistakes yourself and then learn from them? If you try to do that, you are a big fool. So I'm standing here in front of you. We've made some mistakes. There's some learning we have from them. And I'm ready to share that learning with you. But you want to watch something else. So you choose. You can have all these failures for yourself on silicon, or by the virtue of this knowledge and understanding, you can yourself avoid them. Your choice.
So what the two port today's constraints and two ports are actually being slower than the single port. We're talking about in terms of if we access in terms of one port access kind of range.
Madhav, okay, so when we will look at the self-timing part of it, जो हमने बताया था कि reset comes या SAEN comes. Now, SAN arrival, I'm accessing port A. At port A, do I know that port B is being accessed or not? I'm on one side of the memory. Port B may or may not come. Even if it is not there at the time when I started, the clock may come just afterwards. Can I know? So can I now size or time my circuit such that, oh, अगर दूसरा पोर्ट आया तो delay the on time. दूसरा पोर्ट से access नहीं आया तो turn it on early. Can I do that? So sense amplifier is going to turn on only late, assuming both ports are getting selected. So the memory is going to be slow, even if only one port is being selected. Yeah, it will not fail. Probability of failure will reduce because there's much more margin now. But you have to design according to the worst case.
So, the memory में bit cell में तो random data stored है तो हमें कैसे पता चलेगा to avoid coupling कि कौन सा select कौन सा discharge करके रखना कौन सा discharge.
So you cannot design it like that. You have to design in such a way that the worst case coupling you are able to emulate, and you are able to ensure that even in the presence of that worst case coupling, your circuit works. There's no failure. You have to leave that kind of margins in your design. Is that clear? So you cannot anticipate कि यहाँ पे 0 आएगा या यहाँ पे 1 आएगा. No, you can't. You understand your circuit. You see which is the worst case. And then design your stimuli in such a way that that worst case is activated. Design your verification plan in such a way that that worst case is activated. Then something will happen. Is that okay? So then after that, we actually looked at the layout. We looked at layout in far more detail, and you know that we make a lot of design violations in the SRAM cell layout. We saw that in the advanced layouts, there are almost no bends. All the polys were straight, all the actives were straight. We even saw a case where just because there was a notch on the active, irregularity on the active, we saw that, okay, a larger SRAM cell had better median SNM or mean SNM, but in terms of worst case SNM, it was worse than a cell which was fully regular. We also arrived at the conclusion that in advanced technologies, in FinFETs, for example, the cell ratio is maintained as 1 only. It's not possible to do anything else. You can't have a fractional cell ratio in FinFETs, but it's kept to be 1. The only thing you can do about FinFETs is that, okay, length को थोड़ा सा change कर दिया ताकि pass gate is a little more resistive than the pull down. But in terms of width, it is the same. Then we also saw about long contacts. We talked about local interconnect layer. We talked about a lot of things. And we said that these structures and these violations are allowed inside a memory cell, and only inside a memory cell because of the huge repeatable pattern that we are assured of. That it is not that this particular memory cell will now abut with something completely random. All abutments are under my control. Therefore, because everything is physically everything is under control, I can say, okay, now let us not have 2 contacts, let us have a long contact. Are you with me? So just because the structure of the memory cell is repeated millions of times in the same neighborhood, in the same adjacency, we are able to do more violations, or we are able to have more aggressive DRCs than the regular standard cell DRCs. What this also leads to is that since we are violating the DRCs now, the transistor behavior will change. And therefore, SRAM devices, the six devices of the SRAM, have a different model than the regular NMOS and the regular PMOS. How many of you have opened the model file that we have in 65 nanometers? You all worked on 65 nanometer in the DVD course. How many of you have old the spice.lib, the model file? We use NSVT, NHVT, and all that stuff. Hai. Now go open it. And you will see there are additional devices there which are like NPG, HD, something SVT or HVT. That is NMOS, which is used as the pass gate. Then NPD, again HVT or SVT. And then single port ka alag, dual port ka alag. You will find that also. So there are completely different models that we create because these devices are now very, very specific. There are specific violations that are done around them. There are specific anvil proximity effects, stretch effects, a completely different range of things that are to be modeled in these particular devices. So when we go this dense, modeling needs to be done again. It also gives us an advantage because we are now modeling our devices at the exact size. We know we are accurate. So we're not losing or leaving any margins. See, in memories, because you want area is diamond, you want to bring things as close to each other as possible. You do not want anything to be going off the radar. As a designer, you want to have good control over almost every aspect of the design. So now, since the devices are actually characterized and the spice models are made exactly for this particular set of sizes, the accuracy of the CAD results is also superior. So, for example, okay, आप लोगों ने मोंटे कार्लो पावर के लिए चलाया था, कुछ लोग बिल्कुल अरे सर क्यों उस बात को छेड़ते रहते हो बार बार, हाँ? So, but those of you who did for timings, those were all logic cells that we were talking about. Logic cells may, on silicon, if you pick up the silicon, so whenever you join, whichever company you join, know that there is the spice cards are validated based on some standard metrics. Okay. So you put a size of 0.64. Your friend puts a size of 0.68. Another friend puts a size of 0.72. Now, do you think that the device modeling team has put every possible size on silicon to build a model for you? No. They made a size 0.2, they made another size 0.5, they made another size 1, they made another size 2, then 5, then 10. किसी कंपनी ने 5 बनाया ही नहीं, सीधा 10 पे चले गए. So they assume linearity, piecewise linear. Okay. So, but with piecewise linear, what happens? In the middle of that piecewise linear, you have the possibility of maximum error. So you need to leave more margins. But for memory cells, because now we know this is the device size, this is the width, this is the length, and this is where the spacing is to be. We actually have exact models. The margins that you need to leave reduce. Monte Carlo that you do is more accurate. Are you with me? So this is also a consequence of a very dense layout that we make for the SRAM cells. Unlike standard cells, there is a very strong focus on sharing of features across the cell boundary so that the overall area of the cell can be reduced. Sharing तो आप लोग जानते हैं. है ना? कितनी बार असाइनमेंट शेयर करी हैं, नोट शेयर करे हैं. Sharing reduces effort, makes things easier. So we want to do more sharing in memory cells, not in the memory course, memory cells. Okay?
There was a question in the last quiz that which the RC violations we can find when we sell what the advantages of the optimization. So one correct answer was the minimum metal to metal DRC. So we actually did that because like we were not covering the whole contact because of the metal to metal DRC. So
Yeah. So you, okay, look at it like this. Uh, you were not covering the full contact. It means there was some extra resistance that was going to be there. How much extra resistance do you allow? So you violate that distance also. Then you say, okay, contact का coverage भी कम करो. सारा burden एक, you don't put all the burden on only one DRC. You want to reduce the height there. So you see that, okay, if I keep the same metal to metal, I can't get it. If I put everything on the metal to metal, then there is a risk of short happening. So I will take something away from metal to metal. Then I will take something away from contact coverage also. There is also another DRC on minimum area that you can have for a metal stub. There is also another DRC violation on the spacing between the actives and the end well. So you do whatever you can because it's a very systematic structure and because you know that you are anyways going to characterize the particular cell, each device in the particular cell separately. So you go ahead and do many violations there. Okay. So now the assignment that was given to you, bump estimation. Have you done that? So how many of you were able to put it in a MATLAB or XLS and estimate with various combinations that we have in the lecture? You were able to do? Okay. And what were the key findings there? So anyway, the derivation I've already put on the Google Classroom. For those of you who have checked, I've already put the derivation on the Google Classroom. So it's already there in the recorded lectures also. We don't need to spend any more time on it in the class. What we can do is we can directly jump over to the impact of various parameters in those equations. Is it okay if we do that? Those of you who are in the habit of not watching the lectures or not reading, going to the classroom after the class also, can you please go and check this? You're no longer little babies who have to be fed, spoon fed everything. You have your hands, you can pick up stuff and read and study. Please do that. So, impact of cell ratio. We said that cell ratio is resistivity of, so width and length of pull down upon width and length of pass gate. And in the earlier sessions, we agreed that pull down has to be less resistive, so it has to be bigger than the pass gate. So cell ratio is expected to be a little more than 1. How much more than 1? We do not know, but more than 1. So if you go into that equation, cell ratio does prominently stand out. How many of you seen that? मतलब देखा derive नहीं भी करा तो lecture में तो सब कुछ solved है. How many of you have seen at least that much? Even if you did not derive, it's fine. But at least you've seen this. So cell ratio has a significant role to play. And what we notice is that when the cell ratio is 1.5, V bump is 82. You reduce the cell ratio to 1, the pump goes up to almost 120. That is 50% larger bump. That 40 millivolts is immediately eroded from your SNM. Now let us go overboard and we put the cell ratio to be 3. doubled, doubled the size, but the gain is not equivalent. By kind of reducing the size, you had a loss of 40 millivolts. By doubling the size, you gain only, you know, 35 something millivolts or 40 millivolts again. Not much. And then there is also the risk of the trip point going too low and the stability going for a toss. See, we are just looking half the picture here. Just looking at V bump. In reality, there is a latch. So the other transistor, the inverter also can trip because you have such a skewed pull up to pull down ratio there. So there is a sweet spot. You know, you would typically not go for a cell ratio beyond 1.75. It is a lot of area lost, and the gain in stability is also not much. Okay. And on the lower side, as we discussed, one log rakh rahe hain abhi because FinFET demands that. Otherwise, 1.25. So if you're not in a FinFET technology, 1.25 is still something that you would want to maintain, not go lower than that. Okay. Coming to mismatch, what happens when mismatch comes in? So we have kept the cell ratio at 1.5. Our original thing was 82 millivolts. With just pass gate being a little faster, I lose 13 millivolts. That's almost 16% loss. Then more than 16% loss. Then if I go to pull down, also being a little slower, 110 approximately. And if 3 sigma is not sufficient, see 3 sigma and 3 sigma, what is the cumulative sigma that you are covering? 3 and 3 ke saath. So how do you find the effective sigma? Under root of sigma 1 square plus sigma 2 square. Under root of 18. So you are only at 4.25 something. But in memories, you know, you have to cover at least 6 sigma. So this doesn't work. So what you say, okay, let's go to 4.5 sigma, 4.5 sigma on each side. That is when you go to something like 6 sigma in total. Okay. So if I really have to qualify 6 sigma, then I'm as bad, in fact, a little worse than when I had kept the stage ratio of 1. Are you able to see this? And do you relate to that graph that we had? That the worst case is actually bad. Now, if the stage ratio was 1 and there was a completely straight active, no bends and nothing, some variations would have reduced. So sigma would have been a little lower. And that is why there is a very strong focus when we design SRAM cells on not having too many bends or turns or anything like that. That is where this particular layout topology that we discussed in the class is the most widely used one today. Okay? Yeah, अभी तो हम खाली worst SNM की तरफ जा रहे हैं ना. So we're going 6 sigma on the worst side. Then you go 6 sigma on the other side and that will be worst for the right margin.
You have taken minus 4.5 for this side, and then plus 4.5 for the positive side.
No. Wait. What have I done? Be careful. Thank you for asking this, Arpit, because this confusion should not stay. I have made pass gate faster. I have reduced its VT. Why? Because I know that a faster pass gate would degrade my SNM. What have I done to the pull down? I have not made it faster. I have made it slower. What have I done? I have put that 4.5 sigma higher VT. But this point is still 6 sigma away from the nominal. Root of 4.5 square plus 4.5 square. That is still 6 sigma away from the nominal. Nominal of what? If it was a nominal SNM, then 6 sigma away SNM would look something like this. Now, can it happen that pass gate is 4.5 sigma slower instead of faster? Can it happen like that?
Yes.
Yes. In some particular cell, that can be the case. And in that particular cell, can it have also happen that pull down is also 4.5 sigma faster than the nominal? Yes. So that is also one case. But that is not the worst case for my SNM. That's the worst case for my writability. So in totality, I would need to cover 12 sigma, 6 sigma on this side, 6 sigma on that side. But on the worst side, I will go only 6 sigma. That's sufficient. Otherwise, I will not be able to design anything at all. Already seen 6 sigma pe jaake I am worse than the nominal of cell ratio 1. If I go to 12 sigma, where will I be?
So that 12 sigma accounts for both the
Positive lobe and the negative lobe. Okay. So this is unlike, how many of you have heard this term 6 sigma for 6 sigma quality for software? You've heard this term 6 sigma quality for software? So they talk about 3 sigma on this side, 3 sigma on that side, and then they say 6 sigma. We are saying 6 sigma on one side for the memory. So we are very, very quality conscious when we do memory design. You do a small mistake and the entire chip goes into the trash bin. Okay? Significant yield losses can happen if you do not take care of 6 sigma on each side when you're designing memories. So 6 sigma software se confuse nahi hona yahan pe. 6 sigma software is 3 on this, total 6. But 6 sigma in memory design is 6 sigma on each side. Okay? So then what happens with the supply voltage? What happens? So see over here, when I say supply voltage, I'm assuming that bit line, word line, everything is at the same voltage. And you will notice that with supply voltage degradation, the bump actually goes up. So in yesterday's quiz, when I was reviewing the quiz for the first time, so when the quiz comes, I have to review and see that everything is fine. So there was this misunderstanding that the TA had that, oh, low voltage means lower bump. We'll just see a case where low voltage means lower bump, because I could read that in the explanation. But the way the question was framed, it was wrong. So I had to change that. So low voltage means lesser stability. Low voltage also means lesser writability. Okay, low voltage is a death knell for memory operation. So in any particular design, you will see that VDD min of the memory, the minimum supply voltage that the memory needs, is higher than the VDD min of any other logic. Because logic, in inverter will work fine even at 0.2 volts. It is a comparison between the subthreshold strength of the PMOS and the subthreshold strength of the NMOS. The trip point may change because of the mobility changes, whatever, but it will still work. But a memory cell is not just about it's not a CMOS logic that we're talking about in a memory cell. It's an analog circuit. So at low voltages, it goes for a toss, both writability and readability. So what do we need to do? We need to put in place what we call as assist schemes. So what did we do? We said, okay, at 0.7 volts itself, if I have to operate, and I lower the word line, you see the bump immediately improves. If I lower it further, the bump improves further. But what happens when this happens? If I apply a word line underdrive, so this is called as a word line underdrive write assist scheme. Read assist scheme. Word line underdrive, read assist scheme. So what happens?
Basket become more
The pass gate becomes very, very resistive. So
cell current
cell current goes for a toss. So क्विज के रिजल्ट्स शेयर हो चुके हैं. तो अगर आपने रूब्रिक देखा हो तो रूब्रिक में आई हैव ऑलरेडी एक्सप्लेन दिस. हाउ मेनी ऑफ यू रीड द रूब्रिक्स फॉर आंसर्स दैट यू हैव डन राइट आल्सो? अरे ऐसा होता तो नहीं है. आंसर दैट यू हैव डन राइट उसका रूब्रिक कौन देखता है? बड़े जुझारू बच्चे हो भाई, बहुत अच्छी बात है. तो देखो प्लीज देखा करो बिकॉज द रूब्रिक हैज मच मोर इंफॉर्मेशन दैन द क्वेश्चन. क्वेश्चन सही भी आता हो तो वी आर स्टिल एक्सटेंडिंग beyond what the obvious answer is when we write the rubrics. Okay, so at least I pay a lot of attention to that. So if you read the rubrics, it will help you. And this is what we talked about in the rubric also yesterday, that this is a word line underdrive read assist scheme, but the read current goes for a toss. It's thrown out of the window. So it's not 200 millivolt lowering of word line, even though it brings me that same stability. It's not what I can really do. I have to do a little bit of word line lowering, but that will not allow me to go to 0.7 volts over here. Okay. So let's look at what other levers I have. Okay, there is this level of ground. If I can take ground to a lower voltage than 0, then again I start to gain on V bump. Now, sir, negative voltage generate करना पड़ेगा क्या? See, look at it like this. In our circuits, everything is actually relative. If you do not generate a negative voltage, or if you do not want to generate a negative voltage, you operate, let us say, the VDD at 5 volts, but GND is at 4 volts. What is the effective VDD the memory cell is operating at? 1. Now, instead of 4, you go to 3.8. So for that particular memory, it is a minus 0.2 level. But this requires a top level, a global level kind of a thing. Globally, आपको पता होना चाहिए that memory VSS has to be managed like this. This is a huge overhead at the system level. So it is not that you have to always generate the negative voltage. You might just have it on your chip. But if you have to generate, then you use flash pumps. We'll cover them in a little detail when we come to DRAMs. Okay. Now, what is the impact of threshold voltage? So we have chosen two different threshold voltages. One is with let us say a standard VT, and the other one is with a high VT. And you see that, okay, with high VT, the stability goes a little worse. The bump goes a little higher. So what does this tell you? That if you have to design a very low voltage memory cell or a very low voltage memory, you will probably want to use a SVT memory cell. It will be more stable. Now, what we also do is that, okay, do I really need the full cell to be SVT? Or can I just do an SVT on the PMOS? What I have not shown in the slides is what happens when you just lower the bit line voltage. अभी हमने word line voltage को lower करा, but if you just lower the bit line voltage, what have you done? When you lower the bit line voltage, you have reduced the differential that has to be built across the potential divider. So the Vx will reduce. Now, if you have actually written, solved those equations that we talked about and that are already solved to some extent in the artifact that I have uploaded on Google Classroom, you will see that those equations will tell you what are the various assist schemes that you can design. Because the derivation that is given in Veste or Rabi, that is about all VDDs being same, all VTs being same. Now we see, oh, I can do play with something. Those of you who have those equations with yourself and model them on XLS, just see what happens if the PMOS VT is a little higher. अच्छा अभी आपको दिख नहीं रहा, writability पे जाएंगे तो आपको दिखेगा. If the PMOS VT is a little higher and the NMOS VT is a little lower, and what happens when it is vice versa? Just play. See, if you build a model, if you build an equation, then you have a model. You don't need to really do those simulations and check things out. You can be much, much faster. That's the benefit of making models. So then we looked at, there was the other assignment was about estimating the writability of the cell. And we look at them. वहां पे हमने cell ratio से शुरू करा था. Here we start by looking at the impact of pull-up ratio. Now, what is the pull-up ratio? Pull-up ratio is the strength of or W by L of the PMOS upon the W by L of the pass gate. So you want the PMOS to be weak. Why do you want the PMOS to be weak? Because you want the PMOS to give lesser charge on the side where you are discharging the internal node. Are you with me? So you want it to fight less. So you want the PMOS to be weak. So pull-up ratio has to be less than 1. This I'm not telling you. You can actually, if you look at the equations will tell you that the ratio has to be less than 1. Okay? I'm giving you an intuitive feel in the class, but the equations will give you the logical and the exact mathematical reason why they have to be lesser. Those of you who want to understand it in a mathematical way, you should do the derivation. So we did a pull-up ratio of 0.5. The internal node, actually, we were able to pull it down to 30 millivolts. I said, let me make the PMOS strong. What happens? Internal node, I'm able to discharge only up to 128. So what is the consequence of internal node not discharging to very low voltage? The other PMOS will not turn on. The latching action will not start. It's a latch. If you do not have sufficient VGS for the other side, the PMOS is already weak. If you do not have sufficient VGS on the other side, it will not write. So there's a risk that the write will not happen. And if you improve the pull-up ratio, take it down to 0.25, again, you further gains. But what is the consequence of such a bad pull-up ratio? What does it impact? Sorry? Writability तो मैंने देखा VINT कम हो रहा है further. I went to 0.25, so VINT has reduced further. So writability in those terms has improved. What goes for a toss? See, there are no free lunches. What have you compromised when you did this? Huh? I've only made my pull-up still smaller. I have gained the area. Which figure of merit degraded when I improved writability? Right time. Because now my pull-up is very, very small. At low voltages, when I try to write, this pull-up, even if it is fully turned on, it is so small, it will take a long time to charge the internal node to 1. Okay? So what is the impact of mismatch? A 50% loss. Very similar to read side पे भी हमने देखा था 50% loss of stability. यहाँ पे भी हमें दिख रहा है 50% loss of writability because of mismatch. Now, these are just cartoon numbers. These are just anything that I've just put in my model. They are influenced by silicon. They are realistic enough, but they're not exact. Every technology would have their own exact numbers there. But this is just to give you that feel that what happens due to mismatch? All those gains of sizing that you did, mismatch can completely undo them. So for memory designers, reducing mismatch is a huge, huge, huge priority. Therefore, we will actually spend one full lecture on mismatch, more than one lecture probably on mismatch, how to handle it. Many times you can't handle it, but okay, still, at least understanding it will help us to do something about it. Hmm. Then supply voltage. What would happen if supply voltage reduces? See, जब VDD बड़ा होगा तो खराब हो रहा है, but you see VDD कम गया तो भी खराब हो गया. Remember I told you that as you reduce the supply voltage, both writability or stability and writability go for a toss. That is evident over here. Are you able to see this?
Here the cell XU is 1.5. So first we calculated the VX, optimized VX from VX. Then we calculate the right.
Yes. So you did the equation works thing. Then you will note that Vx you need to do. You have to know the Vx to be able to do something on the right side. So Vx you already fixed. Okay.
First we optimized read, then we come.
First we ensured stability. That locker, no one can enter into my locker if I do not allow. Even if someone enters, they're not able to take things away. First I ensure that. Only after that is done, I say, okay, now let me place something inside my locker. So writability comes after that. Is that okay? So then we look at impact of supply lowering only on the array. So what have we done? When all the three were equal, array supply, word line voltage, bit line voltage, all three were equal, we had Vint of 63. We just saw that. I say that, okay, let me take my array to 0.6. What happened? Now my PMOS has become weak because I've lowered the array supply. And my word line is still at 0.7. So my pass gate has not degraded, but my PMOS has now, I have consciously made it weaker. So we introduced. Let me go further. Oh, this happens still more. But now, what is the challenge here again? Right time. Right time. And also, what about the stability of other cells which were in the same column? So you remember we in the layout, see, we covered layout before this. Why? Because you know that in the layout, VDD was run vertically in metal 2. Now I'm saying I'm reducing the VDD of the array by 0.2 volts में reduce कर दे रहा हूं. This was the cell in which I wanted to write. But I have to reduce VDD of all the cells. What about the stability of this one? If by chance my array lowering goes lower than VRET, I'm done. Even the cells which I was not accessing, they will lose their contents. Just so that I'm able to write into this particular cell, all the other cells in the column are at risk. Are you able to sense that even though I'm talking about one memory cell, it is not just one memory cell that I need to take care of? Whether it was about read currents and coupling and precharge and anything, I have to take care of the entire array in one go. Are you able to see that? So array lowering helps. What about word line level? Word line lowering improved? Word line lowering improved? stability. So to improve writability, what would you want to do? Word line overdrive. But what will it do? What is the negative consequence of this? The partially selected cells. Now, अभी हमने पहले रो देखा था, पहले कॉलम देखा था, अब देखो इस रो में. The other cells in the same row. You wanted to lower the word line so that they remain stable. Now you've boosted it. So their stability goes for a toss. Are you able to see that tussle between write and read? You improve one, the other goes for a toss. You improve the other, the first one goes for a toss. And that is the challenge of memory design. That is why when you do this course, you're kind of making your career AI proof. AI will not be able to handle this so easily. It can assist you, but still you have to take the call, provided you know what call needs to be taken. So it is important to understand the entire systemic view when you're designing stuff.
How does that sense of stability affected by the
Lowering नहीं, यहाँ पे आप पढ़ा रहे हो word line को.
how it is affected?
So you tell me, I have mux 4. I was writing into this particular cell. There are other 3 cells for whom again word line is now at 0.9 volts. And array and everything else is at 0.7. What would happen? Abhi, during the read or stability part, what did we say? That at 0.7, if I need to improve the stability, what do I need to do? I need to take word line to 0.5. Remember? Now I'm taking word line to 0.9 instead. What would happen? Just you have the equation with you. Just do the analysis. You will see that the bump will go up. See, what supports write obviously doesn't support not write. Stability means not write. I'm making write easier. So not write is definitely going to go worse. Are you able to see this yet? No. Okay. If I take word line to 0.9, what happens to the resistivity of the pass gate? I've improved its VGS. The gate voltage has gone to 0.9. The source voltage is still at 0. The VGS has improved. What would happen to the current that can flow through the pass gate? More current can flow. What have you done something to the pull down yet? Have you done something to the pull down? So pull down can sink only that amount of current that was there earlier. So what will happen? There's more charge flowing from the bit line, but it has nowhere to go. Where it go? It will accumulate.
VX?
Vx will rise. Vx rising means stability degraded. Are you able to see this now? ठीक है सबके लिए? Now again, impact of VSS. What happens? So now in read, you wanted to take VSS to a negative level because you wanted to make the latch stable. Over here, you want to take VSS to a positive level so that you're able to go to a lower V-end. The latch becomes unstable. Again, completely opposite constraints. Impact of VTH. Here again, high VT means worse writability. High VT and low VDD, they have similar impact on both read and write operations. They degrade it.
IVT of basket or
High VT, generic. Nominal VT is higher. I'm using HVT devices.
the pull up? Then won't we are making the pull up weaker and hence the writability is higher.
But I made the basket also weaker, na? I did not just make pull-up weak, I made pass gate also weak. So now it is the interplay of the two. ऊंट किस तरफ बैठेगा अभी नहीं पता ना, तो आप कैलकुलेट करोगे तब दिखेगा आपको. जो मैंने कैलकुलेट करा उसमें ऐसा दिखा. आपके इक्वेशन में आप अलग वेरिएबल्स यूज करोगे तो कुछ और दिख सकता है. I made some assumptions about the technology. You take a different assumption about the technology. So, such models, if you create such models, they can also be helpful in doing what we call as design technology co-optimization. DTCO is something which is very, very needed today. Because if you just go linearly, you will get stuck into all this. कि अब क्या करूं? Which read assist or which write assist scheme to use? Whatever I use, it's, एक तरफ कुआं दूसरी तरफ खाई. It's not leading to where I want to be. The risks are not reducing. I do find a pathway, but then that pathway also leads to a dead end. So that is where then you start to go to the higher level of hierarchy of abstraction and say, okay, let me optimize design and technology together. So I say that VT of the PMOS, okay, let it be just a little bit lower. VT of the pass gate, let it be just this. So you would use different kind of stressors, you use different kind of methods to be able to arrive at the sweet spot that you wanted to be at. So DTCO, Design Technology Co-Optimization, is a term that you will hear very, very often if you go into either standard cell design or analog circuit design. Basically, if you go into full custom design, चाहे standard cell की तरफ, चाहे memory की तरफ, चाहे analog की तरफ, DTCO is something that you will hear very, very often in the advanced technologies. Older technologies, technology and design would work in silos. But today they can no longer work in silos. They have to learn how to work together. They have to learn each other's language. See, that is why those of you who are doing stuff in VLSI and want to be good VLSI designers, whichever place you are in, full custom designer or system designer or architect or whatever, I insist that have a broad range of electives under your belt. See, अभी आप कॉलेज में हैं, अभी आप बहुत ब्रेथ गेन कर सकते हो. If you go into very focused, so Renaissance people had come for hiring your senior batch, and Renaissance tha NXP tha, I don't remember, someone of those had come, and after the interview process they said, "This is very strange. Your entire batch is tuned towards PD, physical design, place and route. Okay, we have PD related jobs, but they don't even know how to write a good Verilog code. Hello? It won't work. It won't work." They said, मैं verification का कुछ पूछ रहा हूँ, they have no clue. Just one thing they know. See, this will anyways happen once you join a job. Your companies will ensure you know only one thing. They will make you forget everything else. You don't do this to yourself. Not yet. You're still in college. Have as much breadth as possible. Really. You should understand what computer architecture is. You should understand what operating systems are. You should understand. So, operating systems are computers, of course. Say yes. But the chips that you design are to be put in computers. If you do not understand how your designs are to be used, you will not understand. When the core design requirement comes, you will not be able to, go halfway and meet them halfway. A good breadth now in these years will lay a foundation for you to be able to do co-design later. That is why I say do that course on physics of semiconductor devices or advanced semiconductor devices. It's important because if you do not understand them and then later you have to optimize your designs, you will not know how to meet halfway in the ground with them and do some co-optimization. It is extremely important. See, if you do not do this, AI will anyways, because AI तो और ज्यादा complexity handle कर सकता है ना आपसे, वो तो machine है. आपके ऊपर इंफॉर्मेशन ओवरलोड हो सकता है। एआई का आप उसको और बड़ा सा कंप्यूट फार्म दे दो, वो कर लेगा, देन यू विल बी एट रिस्क, क्योंकि वो नेचुरली नहीं कर पाएगा, उसको भी ट्रेन करना पड़ेगा हमें, बट वो कर लेगा। लेकिन अगर आप उस जगह पे बैठ जाते हो, then what happens? The need to train the AI, because that's a very complex and a very hefty training, that will not arrive because the problem is not there. But for that, you have to know which how to go halfway up. You have to know the language. You have to know the constraints that they face. For that, at least उनका coursework करो, उन courses में projects करो. It's extremely important. नहीं नहीं सर, उसमें grade अच्छा नहीं आता. अरे damn with the grade यार. Grade आएगा नहीं आएगा doesn't matter. Have you learned? That is what your focus should be. नहीं नहीं, यहाँ मार्क्स तो आ जाते हैं, क्विज के अंदर क्या करना वीडियो देख के, आपस में दोस्तों से डिस्कस करके मार्क्स तो क्विज में आ जाते हैं। यस मार्क्स, बट आपने सीखा क्या? डू नॉट वॉच द वीडियो इवन नाउ। 3 दिन का वीकेंड था, इवन नाउ आई कुड सी ब्लैंक फेसेस व्हेन आई वाज डिस्कसिंग अबाउट द लास्ट लेक्चर। इट वॉन्ट वर्क फॉर यू, इट डजंट वर्क लाइक दैट। सी ज्वेलर्स के पास जाओ ना, सिंधी ज्वेलर्स के पास, और डायमंड ज्वेलरी खरीदने के लिए जाओ, बोलो कि हाँ ये डायमंड इज स्टिल बेटर। सी वी टॉकिंग अबाउट डायमंड्स, मेमोरी एरिया इज डायमंड, हाँ, ये डायमंड इज बेटर, ओ बट दिस इज सो एक्सपेंसिव। वन वेरी कॉमन स्टेटमेंट दे पुट, सर जितना गुड़ डालोगे उतना ही मीठा होगा ना, तो आपको ज्यादा मीठा चाहिए, ज्यादा सुंदर चाहिए, तो और पैसा निकालो। सेम थिंग वर्क्स हियर। The more time you invest in any particular topic, any particular course, the better your understanding would be. जादू से नहीं आएगी, चैट जीपीटी will not give you that understanding. अभी सुबह ही there was a set of final year students who got a terribly bad grade in their BTP. And I said, okay, show me your report. I could see chat GPT. Show me your poster. Again, I could see chat GPT. There were 2 people. One person presented 4 topics. Other person presented only 1 topic. जिसने 4 टॉपिक्स प्रेजेंट करे थे उसको सी दिया, जिसने 1 करा था उसको बी माइनस दिया। क्यों? क्योंकि जिसने 1 टॉपिक प्रेजेंट करा था, दैट पर्सन हैड सिंथेसाइज्ड हिज वर्क बाय हिमसेल्फ। द अदर पर्सन, चैट जीपीटी जिंदाबाद, एवरीथिंग वाज रिटन। This is half an hour video that I have, which I insist my students should watch before they go for the poster presentation. They had not watched that half an hour video also. उसमें clearly लिखा है, the poster has to be a summary. It is not to be detailed. Details are in the report. But this first guy, he presented 4 topics. Everything about the topic was there in the poster. Not developed the skill of synthesizing information by yourself. चाहे जीपीटी कर तो रहा है, वो दिख रहा है हमें फिर। So please do not rely on AI. AI will lead to mental atrophy. Atrophy शब्द पता है आपको? What does atrophy mean? Atrophy. Anyone? No one knows. Okay. Has any one of your family members or someone you know had a paralytic attack? Anyone? Seen some movie जहां पे कुछ paralytic किसी को हुआ हो? So when you do not use your muscles, the muscles die out. किसी का पैर में हाथ में कभी फ्रैक्चर हुआ है? So as soon as you recover from there, they say, let's go to physiotherapy. Why? What has happened? The muscles have got wasted away. You not used them, so the muscles wasted away. That's called atrophy. That's physical atrophy. I'm saying AI and ChatGPT and Gemini are leading to mental atrophy for you. You're killing your mental acumen by depending heavily on AI. Don't do that to yourself. Okay. All the best. We'll start with the ROM cells in the next class. Please be prepared. There will be office hours tomorrow. You can join.